Friends, let us continue our discussion on complex reactions, and we are looking at simple reactions in the sense that they are series parallel model type of reactions, to see what kind of behavior we can expect when we have complex reactions. And in our last session we saw that even a reaction like series reaction A1 going to A2 going to A3, we get yield conversion diagrams which we see in the industrial practice as well. So, fallout of this is typically conversion is often considered as the design criteria, but when we have complex reactions, maximum conversion does not always lead to maximum product or yield of maximum product, and we have to now design our reactors maybe for yield, depending upon what is more important, yield of the desired product or the conversion of a reactant. We also saw that the type of reactor that we can use is not necessarily same when we are maximizing the conversion or when we are maximizing the yield. Let us take this discussion forward and look at two important concepts which are often used in defining the rates of complex reactions. So, as we saw in the previous classes, complex reactions are large number of network of reactions and so on. The question before us is that how do we determine the kinetics of such process? To be more precise, suppose if I have a reactant and it is going to some products, but while going from reactant to products, it undergoes a series of reactions. It could be series, parallel, connected, or complex reactions. So, my interest is to find out what is the rate of consumption of a reactant, what is the rate of consumption of as many reactants as are there, as well as what is the rate of formation of product. Now, one simple way of doing this would be write down in detail all the reactions that you know, then find out the kinetics of each of these process, and then there is nothing to do. You know already what is the rate of consumption of reactants. But it turns out that many of the intermediates, that is between reactant to product, there are several intermediates, and many of these intermediates are not so easily amenable to measurements. So, we cannot really get the kinetics of such processes so quickly or so easily. So, we need some assumptions, some reasonable assumptions which we can justify, so that this whole analysis is simplified to a large extent. So, let us start looking at what kind of assumptions we make, or what kind of approaches that emerge as a result of this assumption. And the first approach that we are going to look at is what we call quasi equilibrium approximation, or QE to be short. So, let us take an example of our reactions which are series reactions, but this time I have made these reactions reversible, and the reason for that will be clear as we discuss. So, now we can start looking at the reaction A1 going to A2. It is a reversible reaction, this one first reaction over here, and then the A2 also goes to A3. That is a second reaction that we have written. Both reactions are reversible, and we are going to restrict our discussion to law of mass action kinetics. So, we can say that both reactions or rather all reactions, forward direction, reverse direction, they are all first order reactions. So, I have two reactions. So, I need two rates R1 and R2, and these are those two rates. R1 is K1 times C1 minus K minus 1 times C1. I am using the subscript minus to denote that it is a backward reaction, and same thing applies to second reaction R2, this should read R2, R2 equal to K2C2 minus K minus 2 C3. C1, C2, C3 are the concentrations of 3 species that we have, A1, A2, A3, A4, sorry A1, A2 and A3. And let us say that these reactions are taking place in a batch reactor. So, what we are going to do is we start writing the mass balances for batch reactor. So, let us do that. So, our first species dC1 dt, what is happening to that? You can go back to your stoichiometric coefficient matrix and rates and so on. That is in a compact form for example, we could write dC dt as nu transpose into R, where our nu is a stoichiometric matrix. We had discussed that earlier. R is my vector of two reaction rates R1 and R2. Okay. Nu is to matrix. If you like, we can write that matrix over here. The first element, first reaction, so stoichiometric coefficient is -1. First reaction, second species A2, so stoichiometric coefficient is 1. A3 does not appear, so it is 0, and second reaction A1 is 0, -1, 1. So, this is my stoichiometric matrix. So, if I take these two things together, I will get my mass balances, and you can verify it for yourself as minus K1 C1 plus K2 K minus 1 C2. That is all that is happening in the for the first species. Similarly, I can write for dC2 dt, I can write for dC3 dt, and then by assigning some suitable values of C1, C2, suitable initial values of C1, C2, that is let us say in this particular case I have taken C1 as 1, C2 as 0.4, C3 as 0. These are some random values that we have given, and some values of the parameter set K1, K minus 1, K2, K minus 2 and so on. So, if you plug these equations or plug these numbers into these mass balances and simulate them, you will get concentration profile which looks something like this. So, what we have is on the x axis is the time. So, this is my time and this is my concentration, and there are 3 species. So, we are showing them by black, red and green lines C1, C2 and C3. So, as the reaction proceeds, A1 decreases, C2 increases, C3 increases, and after certain amount of time, as you can expect from a reaction of this kind, that we reach an equilibrium where there is no further increase or decrease of the species. And we see that C2, C3 are both increasing and both are reaching same value. Now, when we reach equilibrium, remember we said that equilibrium is reached for each of these reactions. So, for example, when equilibrium is reached, R2 is 0. So, we have C3 by C2 as K2 by K minus 2 from this particular reaction, R2 equal to 0, and since I have chosen K2 and K minus 2 values to be unity, we get equal value of C3 and C2, and that is what we see over here. That is the equilibrium value. All right. So, this is one particular scenario. Now, let us look at the same reaction scheme, but with different set of kinetic parameters, and we now simulate this process for K1 1, K minus 1 0.5, K2 K minus 2 both being equal to 10. So, we have a new set of kinetic parameters. My initial conditions are still the same as before, and I find that my final value of C 3 by C 2 is still unity, because if you see here K 2 and K minus 2 both are equal. So, at equilibrium both C 3 and C 2 are equal, and I have the same value of A 1, or C 1 value is same as before. So, initially I started with same initial concentrations, finally I end up with same concentration. So, what is the difference between the two cases, you may ask? If you have noticed my previous curve closely, you would have now realized that for this set of parameters, C 2 and C 3 values are much closer to each other right through the entire time period as compared to the previous case. Let us go back to the previous case. Here, as I said, the final values are same, initial values are same, but C 2 and C 3 values are significantly different for at least quite some time, maybe up to here, and then they merge onto each other. So, that is a difference between these two conditions, these two simulations or these two reactions. Now, why is this happening, or what is the difference between the two cases? We started with the same, we ended up with the same mass balance equations, except kinetic parameter values are different. If you notice here, my kinetic parameter values K 2 and K minus 2 were same order of magnitude as K 1 and K minus 1, 1.51, they are all same order of magnitude, but not in this second case, where K 2 and K minus 2 are roughly 10, whereas K 1 and K minus 1 I have not changed. So, they are same 1, means for this particular case there is a order of magnitude difference between the rate constants of first reaction, and that is this reaction over here and the second reaction over here. In fact, second reaction rate constants are order of magnitude higher than the first reaction rate constant. So, what happens as a result of this? Now, if you look at over here, you forget this initial time period. Okay? Initial time period, there is a difference between C 2 and C 3, but for majority of the rest of the time period, C 2 and C 3 are very close to each other. C 2 and C 3 are very close to each other. Now, if you recall, our equilibrium condition was C 3 by C 2 is K 2 by K minus 2. If C 3 and C 2 are very equal, both are equal, they have to be, because K 2 and K minus 2 are same. So, at long times they have to be equal, but even at short times C 3 and C 2 value are equal, which was not the case in the previous example. C 2 and C 3 were substantially different, or in other words, what is happening here is that even though the reaction is proceeding, how do we know reaction is proceeding? Because everything is changing. C 2 is changing, C 3 is changing, C 1 is changing. Even though reaction is proceeding, there is internally an equilibrium between species 2 and species 3. The entire reaction has not reached equilibrium, that is at this point of time when the equilibrium is reached. But in this region, A2 and A3 has almost reached equilibrium, because according to our parameter values C3 C2 is 1 when that reaction reaches equilibrium. Or in other words, when we had reactions, two reactions with differing order of magnitude of kinetic parameters. That means, second reaction is much faster compared to the first reaction. So, when we had that scenario, we see that second reaction reaches equilibrium, that is C3 by C2 equal to 1 much faster, and for all practical purposes, that is except this time period over here, for the entire time period I can assume that C3 by C2 is almost equal to 1. There may be small variation, but being engineers we always talk about practicality of the situation. So, even though numerically or mathematically speaking there may be difference between C3 and C2, they have reached almost equilibrium. This is what is known as quasi equilibrium approximation. So, let me refresh ourselves what we just now discussed. We have two reactions 1 and 2. These reactions, order of magnitude of their kinetic rate constants are different. For this particular example, reaction 2 is much faster compared to reaction 1. So, when we have a scenario like this, we can invoke what we call a quasi equilibrium approximation, saying that the faster reaction, namely reaction 2, reaches equilibrium in a very short span of time, and therefore, we can assume that this reaction has reached equilibrium, and we invoke the quasi equilibrium approximation. So, what is the basic essential requirement for quasi equilibrium approximation? Among various reactions that we have, some reactions are much faster than other reactions, and those faster reactions reach equilibrium. Now, why we call it quasi equilibrium? Because as you can see here, there is still changing, things are changing with time, our concentrations are changing with time. So, we have not reached equilibrium, a true equilibrium as what is happening at this particular time. So, this is a equilibrium only for one set of reaction and not the entire reaction set, and therefore, we call such approximation quasi equilibrium approximation. So, what happens if you have quasi equilibrium approximation? Now, let me go back to go back to this reaction and write it. Let us say we have A1 going to A2, okay, and A2 going to A3. Now, I am going to slightly make a deviation. I am going to say that my main reactant is A1. A1 is my reactant. It is going to A3, main product, but there is an intermediate A2, and the reaction actually takes place from A1 going to A2, A2 going to A3. So, my interest is to find out what is my rate of consumption of A1 or rate of formation of A3. So, to do this, what I am going to do is that I have my R1 as K1 C1 minus K minus 1 C2, same thing as before. Minus 1 C3. So, now what I will say is that my reaction A2 to A3 goes to equilibrium much faster. So, my quasi equilibrium approximation, because rate constants K1 K minus 1 are much smaller than K2 K minus 2. So, quasi equilibrium approximation for reaction 2, that means R2 is very much close to 0 and C2 K2 C2 is almost same as K minus 2 C3. Okay. So, now what happens? We have now C2 which is approximately equal to K minus 2 by K2 into C3. Now, how does this help? Remember, our reaction network is A1 going to A3 and A2 is an intermediate about which we do not know much. So, if I write my rate of this particular reaction, that will be K1 C1 minus K minus 1 according to this into C2. But if I want to use this, I need a knowledge of C2, and this is the intermediate which I cannot measure, or I do not know what are the rate constants and so on. So, what do? I can write this as K1 C1 minus K minus 1, and for C2 I am going to put K minus 2 by K2 into C3. So, this is K1 C1 minus K minus 1 K minus 2 K2 C3. So, this is my rate of reaction. So, this rate now is known in terms of the concentrations of the species which I am able to measure, because my main reaction is A1 going to A3. So, C1 I am able to measure, C3 I am able to measure. So, I have this particular set of reaction. So, what did we do? We had original reaction, its mechanism is of this kind. So, this reaction actually is not a single step conversion between A3 to A1 to A3 and A3 to A1, but it is a multi-step process, a complex reaction of A1 going to A2, A2 going to A3, and in this complex reaction I want to find out the rate of reaction in terms of concentrations of species A1 and A3. So, I have to look for ways of simplifying this kinetic analysis, and one way I can do that is use quasi equilibrium approximation for reaction 2. This is my reaction 1. I can use it for reaction 2 and express C2 in terms of C3 and put it back in this particular rate expression, and I get my kinetics of the reaction in terms of C1 and C3. So, I have two options actually now. If I want to simulate this particular reaction, I have two options. Number one, I can consider the detailed network, simulate the process, results of which we saw here, or I can invoke quasi equilibrium approximation. So, what do? My dC1 dt is now K1 C1 minus K minus 1 K minus 2 K2 C3, and dC3 dt as you would imagine, it would be exactly negative of dC1 dt. So, what I can do is actually minus dC1 dt if you do all the simplifications. So, what we see here, solid line, same simulations as before, okay, detailed simulation. The dotted lines with quasi equilibrium approximation, and what we can see over here is that, except, so black dotted line and solid line are almost on top of each other. That means, fairly good approximation for C1. For C2 and C3, of course, if you see this red line and this blue line, that is the dotted line for C2, there slightly deviation is there in the beginning, but other than that the behavior is almost exact. So, fairly good approximation, which case in which this reaction is, or second reaction is much faster. So, we can invoke quasi equilibrium approximation. Let us look at the second approach. This is first approach. Let us look at the second approach of simplifying the reactions. This approach is what is known as quasi steady state approximation, or QSS. Earlier one was QE, this is QSS. To illustrate this approximation and to keep matters simple, let us go back to our same reaction, reaction 1, reaction 2. This time I have made them irreversible, but that is not required. We can also do the same exercise with reversible reactions and you will get the same results, or I should say similar results. This particular diagram may have been familiar to you if you recall our previous last session on complex reactions. We had simulated this reaction for ratio of K2 to K1, that is our alpha value, these two rate constants, ratio of that alpha value equal to 5. And you also had seen this, where we said that dC3 dt is almost same as minus dC1 dt. Again, now we will go back to our earlier idea, that is, my reaction of interest is actually this, but there is an intermediate. That intermediate is A2, and the real reaction is not one step conversion of A1 to A3, but rather a two step process of A1 to A2 and A2 to A3. Now, if you look at this alpha equal to 5 result, we see that this A1 and A3 are almost mirror image of each other, or dC3 dt is minus dC1 dt. We had seen that earlier. In fact, where did we see this? We saw this when we discussed the rate determining step concept. Now, if alpha value is large, that means second reaction is much faster than the first reaction. The first reaction is what determines the rate of the reaction, not the faster reaction. But now, let us look at what is happening to C2 and in particular dC2 dt. Now, if you look at the slope of this A2 line and slope of this A1 and A3, which are similar to each other, we see that dC2 dt, or slope of this line, is practically 0 if we compare it with slopes of A1 and A3, or in other words, even though reaction is taking place, A1 is changing with time, A2 is changing with time, A3 is changing with time, A2 is not really changing with time. It is in fact 0 for majority of the times, only this small deviations in the beginning, which implies that we can approximate this as dc to dt equal to 0. What is the condition dc to dt equal to 0? We will arrive at this condition when we reach steady state, or when we reach this condition we say that we have reached steady state. So, as far as A2 is concerned, it is almost at steady state all the time, but that is not the case with C1 and C3, and hence we call this condition as quasi steady state approximation. That is, we can invoke a quasi steady state approximation for species 2 A2 and say that its dynamics is much slower compared to that of A1 and A3, and therefore, say that dc to dt is almost equal to 0. This is what we call quasi steady state approximation. Quasi steady state approximation is invoked for a species, not for a reaction. Quasi equilibrium approximation is invoked for the reaction, not any species, whereas quasi steady state approximation is invoked for the species. Now, what was the condition under which we can invoke this? This was the case when second reaction was much faster than the first reaction. Now, let us look at what is actually happening. A1 is going to A2 at a relatively slower rate, and A2 is going to A3 at a relatively faster rate, which implies that as soon as A2 is formed from A1, it undergoes reaction to form A3. So, hardly anything of A2 is left in the reaction, and we have direct conversion between A1 and A3. Direct conversion in a mathematical sense. Strictly speaking, it is A1 going to chemically, it is A1 going to A2, A2 going to A3, but A2 going to A3 is so fast that we hardly see any accumulation of A2, and we see only A1 and A3 interchanging. So, this is the basis for quasi steady state approximation, or in other words, if I have reactant going to product through several intermediates, and if these intermediates are highly reactive, that means as soon as they are formed, something happens to them, either they go from one form of intermediate to another form, or some of them go to products, various different products, but that conversion process is very fast. If that is the case, then we can invoke quasi steady state approximation for those highly reactive intermediate species. So, how do we use quasi steady state approximation? Let us go back to our reaction set once again, and this time let us say that I have A1 going to A2 going to A3 is my mechanism of the reaction, whereas actual reaction is A1 going to A3. So, now if I write my mass balance equations, we know dC1 dt is minus K1 C1, dC2 dt is K1 C1 minus K2 C2, and dC3 dt is K2 C2. So, now I want to know the rate of formation of my A3, and if I look at that rate of formation, it is actually K2 into C2. So, when if I look at my rate, what is my rate determining step? My rate determining step in this case is the first reaction, but if I want to look at the rate of this reaction, it is actually K2 into C2. Now, I do not know what is this, C2, okay. I do not know what is this C2. So, what I can do is I can invoke quasi steady state approximation for this particular species A2, or this equal to 0. So, if I say that this is equal to 0, then I have K2 C2 is almost same as K1 C1. Therefore, the rate of formation of my product is nothing but K1 into C1. Suppose I make this little more involved, okay, and say that this reaction is reversible. Okay. If that was the case, then I would add K minus 1 into C2, okay, reverse reaction. Then here also I will say minus K minus 1 into C2, and rate of formation is K2 into C2. So, now for this particular reaction, and if I again say that this quasi steady state approximation is invoked for this species 2, then this is almost dc to dt is almost equal to 0, then I have K2 plus K minus 1 into C2 is equal to K1 C1, or C2 is almost equal to K1 by K2 plus K minus 1 into C1, and my rate of formation of A3 is K2 into C2. So, that is K2 into K1 divided by K2 plus K minus 1 into C1. So, this rate of reaction is now known in terms of concentration of one species. Okay. So, this is how we use quasi equilibrium approximation, quasi steady state approximation, quasi equilibrium for the reaction, quasi steady state for the species. So, let us go back to our reaction set once again, and if I invoke quasi steady state approximation and simulate the whole process, I find that my this was when K2 was much higher. So, what we see here is the approximation, that is how C3 is changing. This is the case when K2 is very small, but as we keep on increasing the value of K2, that rate constant, we actually reach the saturation point. So, there are two different ways in which we saw in this particular class how we can simplify the rate of formation of product or species. Let me recap once again, because this is an important concept which we will not be repeating again and again. So, let me recap these two approaches and put them in perspective. So, what is the problem that we are trying to address? We are trying to address, let us say my reaction A1 going to some product. So, let me call give some number, it does not matter. Okay. So, my main reaction is actually A1 going to A10. So, this is my main reactant, this is my product. What is my objective? These are, when I say this, it is implied that I am able to measure my reactants and products. Intermediates are something which I am not able to measure. Okay. So, this reaction from reactant to product actually does not take place as one step process as we saw here, but is actually maybe goes to A2, then A2 goes to A3, A3 combines with A2 to give A4 to A5, A5 A1 combines with A5 and so on. So, complex reaction network. So, strictly speaking, we can say that rate of formation of this product A10. Okay. So, rate of this reaction, okay, this is a reaction or the rate of this formation of this product formation will be, strictly speaking, in general function of A1, A10 and all the intermediates that are there. Okay. But I am not able to measure these intermediates A2, A3, A4 and so on. So, what is my objective? My objective is to express this rate of product formation in terms of things that I can measure, A1, A10 and so on. That means, I want to eliminate all these A2, A3, A4 from my rate expression. So, how do I do that? We saw we can do it in two different ways. Number one, quasi equilibrium approach. Or approximation or QE for short. So, in this approach what do? We say that these reactions, whatever reactions that we see over here, all these reactions over here, all these reactions are at equilibrium. That means, the rates of those reactions is all those A2, A3, those two reaction 2, reaction 3, whatever may be there, they are all 0 and then eliminate A2, A3 and so on. So, this is one approach. What is another approach? The another approach, second approach that we use is quasi steady state approach. Quasi steady state approach or approximation, steady state approach. So, what is that approach? In that approach, we say that these reactants A2, A3, A4 are highly reactive and therefore, they reach quasi steady state much faster compared to some of the reactants and products and so on. So, we write for these highly reactive species dC2 dt is almost 0, dC3 dt is almost 0 and so on, and thereby eliminate C2, C3 or all those reactive intermediates. So, two approaches: quasi equilibrium approach where we set the rates of these reactions to 0, quasi steady state approximation where we set the rate of change of species to 0. That is the difference between the two approaches. We will use both these approaches in the examples which we will see in our next session. We will see examples of chain reactions, polymerizations, catalysis and so on. So, these are the two approaches which we use for determining the rates of these complex reactions. Thank you.